In the second part of the lab, we had a track that looked something like this. And what we were doing is we wanted to predict for a loop that has a radius r, what would be the required height of release of the object so that it will just make it around that loop. And so we were starting the ball at some height h above the bottom, and we wanted it to, when it got to the top of that loop, to continue going through the loop. And so in order to do this, we had to write a conservation of energy equation, EI equals EF, in which we are saying the initial position is at the top of the track here at position 1. And so at the top of the track, the ball is not moving. It only has gravitational potential energy. And so I'm going to write UGI for the initial gravitational potential energy. And then when it reaches position 2 at the top of the loop, it has gravitational potential energy because it is above h equals 0, which I'm going to define just here at the bottom level portion of the track. So it is a height above that, and so it does have gravitational potential energy, UGF, plus some kinetic energy, because we know that if the ball is going to be moving around that loop, then it must have some kinetic energy, so KF. For the first term in that equation, I'm just going to write mgh, because in my picture I've drawn that lowercase h as the height of the ball at the top of the track. Then for the right side of the equation, I have two terms. The first term is the gravitational potential energy due to its height at the top of the loop. And it's not so quick that we can notice that the height when it is at the top of the loop is twice the radius of the circle. And so if you imagine the radius being here in the bottom half of the circle, and then that radius again extending up to the top of the circle, then the height that it has in terms of r would just be 2r when it's at the top of the track. And so for the final gravitational potential energy, I'm going to write mg2r. The height is 2r. And then for the last term, for the kinetic energy, it would be 1/2 mv squared. And so what I'd like to do next is figure out, in terms of other variables like r, can we figure out an expression for v so that way we can substitute that in and reduce the equation down a lot further. And so what I'm going to do is I'm going to draw the ball at the top of the track down here with this blue dot, and I'm going to recognize that at that point there are two forces that act on the object. There's the weight of the ball, mg, and there's the normal force, n, that act on the ball. And if that ball is moving around in that circular loop, then at that top point there must be a centripetal acceleration that points downwards. And so I can write, using Newton's second law, F equals ma, that n plus mg must be equal to mv squared over r. I've made n, mg, and the centripetal acceleration all positive. They all point downwards, so they should all have the same sign. And so if that ball was released from a height such that it just makes it around the loop, then what we really mean is we want to release it from a height where it makes it around the loop, but just barely, which means that this normal force at the top of the loop would be practically 0. It would barely be in contact with the loop at the top. And so I'm going to set n equal to 0, and I'm going to solve this for v. When we do that, we should find, well, first we could write that mg is just equal to mv squared over r. And I think that after the masses cancel, the velocity is equal to the square root of r times g. Okay, so now I am taking that expression and I'm substituting it back into my conservation of energy equation at the top. So I have mgh equals mg times 2r plus 1/2 m. And now v squared, my expression for v is the square root of r times g. So when I square that, I'll just get r times g. All right, and now most of these terms have a lot in common, and so there's a lot of reducing that I can do here. Every term has m and g in it, so I can cancel all of those. And what I'm left with is h equals 2r plus h equals 2r plus 1/2 r. And so 2r plus 1/2 r is equal to 5/2 r. So h equals 5/2 r. And this is a very exciting result because there's no reason why it has to be 5/2 r. There's no intuitive reason why that 5/2 should be out in front of that r. But what this tells us is, from this conservation of energy equation, is that if I know the radius of that loop, then I know the height that I need to release it from in order to make it around that loop. And that amount is 5/2 the radius of that circle. And so for any radius, I multiply by 5, divide by 2, and that should be the height above the bottom of the loop that I can release that ball from, and it makes it around. But what we found when we actually did this is that due to some things that we were not accounting for in our equations, the ball does not actually make it around the loop. And so we have to raise it up a little bit from there in order to make it completely around. And that is something that we will discuss more in the future.